November 12th, 2015. I'm in this book again, The Story of Measurement. And on this page, 93, temperature and energy. There are a few important concepts I want to overview regarding this and in its relation to the theory of stellar metamorphosis. Temperature began to be measured on the Fahrenheit and Celsius scales in the 18th century, without understanding its scientific relationship to heat. Then an efficient steam engine was invented by James Watt and theorized by Sadi Carnot. And Kelvin, I don't think I'm pronouncing Carnot name correctly, and Kelvin proposed the idea of absolute zero. In the second half of the 19th century, the kinetic theory of heat and temperature and the laws of thermodynamics were formulated. You see James Watt, he lived from 1736 to 1819. There he is working on his little experiments. They account for familiar observations such as that a cup of hot tea spontaneously cools while a cup of cold tea never warms. That's very, very important. That a common salt crystal spontaneously dissolves in water but never spontaneously undissolves. I have to think about that one for the future. That no engine can convert fuel energy into work, its mechanical equivalent, with 100% efficiency. But Mother Nature does things 100% efficiently. Basically, the first law states that heat and work are equivalent, and that the principle of the conservation of energy is correct for a closed system. The second law, the best known, states that heat does not spontaneously pass from a cooler to a hotter body, or alternatively, that the energy in a closed system will inevitably tend to become distributed in the most probable or disordered pattern. The third law states that it is impossible to reach the temperature of a system to absolute zero in a finite number of operations. Therefore, the first law, heat can be converted into work. The second law, but completely only at absolute zero. And the third law, an absolute zero is unattainable, which is Peter Atkins' sardonic summary in his book, The Second Law. Temperature and energy are elusive concepts. A single atom cannot, or a molecule cannot have a temperature, only an assemblage can. Even then, the temperature cannot be measured directly. It must be measured indirectly by the height of a mercury column, for instance. When we say a mercury in a thermostat is at the temperature of the surrounding air, we really mean that the average energy of the mercury atoms must neither be great nor less than the average kinetic energy of all the air molecules. Energy, measured in joules, is not a substance, but a mathematical abstraction. That's very important. You see in a lot of literature that they say pure energy, but it makes no physical sense to speak of pure energy. When you see ideas written inside of articles and scientific pages and things, they say pure energy. There's no such thing as pure energy. It's a mathematical abstraction. So, you know, like that one interview with Richard Feynman where he's like, we don't know what energy is. Of course you don't know what energy is. Pure energy is a mathematical abstraction. It doesn't exist. Its forms include kinetic energy, electrical, and gravitational. Energy was first defined in this sense by Thomas Young in 1807. Since the height to which a body will rise perpendicularly is as the square of its velocity, it will preserve a tendency to rise to a height which is as the square of the velocity. The same idea is somewhat more concisely expressed by the term energy. So it made a really wordy way of saying energy. Hence the fact that stopping distance of a car is not proportional to its speed, but to the square of its speed, in other words, to its kinetic energy. I think that's a very important understanding to have. A lot of people, they don't understand the kind of violence that's in your car as proposed to the surrounding area when you go 5 miles an hour versus 10 miles an hour. And then, you know, 10 versus 20 miles an hour, 20 to 40 miles an hour, 40 to 80 miles an hour. The energy inside the car, of course, it's a mathematical abstraction, obviously, but the rate at which the car is traveling, the energy doesn't increase per however fast you're going. The energy increases at a square of the velocity. So in other words, you carry twice as much energy when you go twice as fast. And then it goes twice again and then twice again. So yeah, when you get into a car accident going 35 miles an hour, that's why it seems so incredibly violent. And then when you get into a car accident going 70, there probably won't be any survivors. Another idea in here I wanted to overview with stellar metamorphosis in particular is the familiar observation that a cup of hot tea spontaneously cools while a cup of cold tea never warms. That's very important. When you look up at the stars in the night sky, you have to understand that they're cooling very, very slowly. They're not going to spontaneously get hotter and hotter and hotter. That doesn't make any sense thermodynamically because it's irradiating the heat away into the vacuum. As well, the star is losing a lot of mass to its solar wind and to flaring and, you know, coronal mass ejections. So, in other words, you have the sun losing mass and losing energy and cooling, meaning if the sun loses mass, loses energy, and cools, as stated by the second law of thermodynamics, what will happen to it? Are there objects that are smaller, cooler, and have less mass? Yes, we call them orange dwarfs. And then what happens if we have an orange dwarf losing mass, energy, and heat, and cooling considerably? What would you find? Well, do we find any of those objects? Yes, they're called red dwarfs. And what happens if that continues on? Well, you have brown dwarfs, and you have blue dwarfs, and you have eventually the leftover object that has differentiated in its interior. We call those planets. But as Michael Z had pointed out that we should call them astrons. You have young astrons, which are called stars, and old astrons, which you call planets. They're one and the same. But we should know that stars cool because that's what they spontaneously do. They don't spontaneously get hotter and hotter and hotter. So to think of evolution in terms of it's really hot and plasmatic to it becomes gaseous and cool and small to it becomes rocky, that's the correct path. The incorrect path would violate the second law of thermodynamics, in which the Earth, as it is right now, will become completely gaseous and then turn into a plasmatic object. That's not the correct path. That would be like saying a large tree shrinks and shrinks and shrinks and becomes an acorn, a single acorn. Or a human, like me, I shrink and shrink and shrink and become an embryo one day. See how that's backwards? Same thing with stars. They don't get bigger and bigger and bigger and become gaseous and plasmatic from their solid rocky state. The solid rocky state is the end state. That's the path. As well, I would suggest for my readers to understand horsepower and watts and joules in the SI system. I'm learning a lot about that inside of my work when I sell electrical equipment, when I have to do conversions of horsepower and how much energy they need and what the amperage rating on it, what's the voltage ratings on all these contactors and, you know, transformers and things that I work with. I'll go ahead and read this little black part right here too, just to... James Watt, inventor of the first practical and efficient steam engine. Watt's first steam engine, built in 1769, improved on the design of Thomas Newcomen by introducing a separate steam condenser so that the piston could keep hot while the condenser was kept cool. He also coined the unit of horsepower for measuring engine power by measuring the way at which horses could do work. In today's SI system, The unit of power is named the watt. 1 watt is the power when work of 1 joule is done in 1 second, so it's a rate. Or an equal heat transfer occurs in 1 second. 1 horsepower is equal to 745.7 watts. So horsepower is a lot. 1 horsepower is a lot. Now, when you look at cars as well, I learned this when I was, younger. The car engine, they rate a car at 400 horsepower or whatever. But I think the correct way of rating that is bhp, which is brake horsepower. But in other words, you have the amount of horsepower that the car produces, but a lot of that heat that the engine produces is lost. So it's not rated at that horsepower. So say if you have like a engine that's rated at 106 horsepower, you have to keep in mind that it's not going to be completely efficient. Just like in these laws of state, it's not 100% efficient unless it was at absolute zero. Which means the 106 horsepower, the amount of friction between the gears and all the pistons and the transmission, and then you have to get it to the wheel to turn the wheel. It's only, maybe like rated at around 55 to 60 horsepower is actually going to moving the car. But alright, I think that's enough on temperature and energy and relating some of the ideas I had. If you have any comments or questions, please leave them below.